Hi everyone. In this video we're going to cover section 9.2, estimating a population mean. And our goal in this section is to estimate the value of an unknown population mean, right? That's what we want to do. We want to take sample data, sample mean, and use it to make a prediction, to make a statement about the population mean. And we once again define point estimate. That is our statistic that estimates the parameter. In this case, it's the sample mean, estimating the population mean. We start out with a little example. We're given 13 randomly selected cars and their fuel economy in miles per gallon. Fuel economy in miles per gallon. And we want to get our point estimate for the population mean. That is X bar. We add all 13 of those numbers together, divide by 13, and you get 24.13. Okay, 24.13 is the sample mean. That is a statement about those 13 cars. But then we take and create a confidence interval, add or subtract a margin of error, and create an interval of numbers. And we use that to make a statement about the population of all cars and their fuel economy. Okay, so that's the idea. Same kind of concept as the last section, but now it's using means, not proportions, not percentages. Okay, the only issue, okay, and that's what it says at the bottom here. The issue with creating confidence intervals from sample data, and this comes from the early 1900s. There's a little blurb in the book about this guy. His name was William Gossett, and he worked for the Guinness Brewery. What's that, in like Ireland or something? It's a European country. He worked for Guinness, and he was in charge of doing experiments at the brewery to identify the best kind of barley. Okay, kind of cool job to have in the early 1900s, I think. When working with beer, he was limited to small data sets, and he used the standard normal model, as we did previously, because that's all that was available at that time. And he found that his sample, his confidence interval didn't include the population mean often enough, not at the right rate. And so because he found this irregularity with using the normal model, he created his own distribution, created his own model, and he called it, and he had to use a pen name because Guinness wouldn't even let him publish in his own name. They were really secretive about their stuff. So he created a distribution called the T distribution, students T distribution. And we'll look at that table in just a little bit. But first, we'll put up some properties of the T distribution. It's different for different degrees of freedom, and that's one really important one. The degrees of freedom is your sample size minus 1, little n minus 1. So the distribution changes depending on how many individuals are in your sample. Similar to the normal distribution, it's centered at 0, symmetric about on either side of 0. Area under the curve is 1, so we can apply percentages to it. As t increases or decreases without bound, it never touches the axis. It never equals 0 to allow for those really extremely high but really unlikely scenarios. And then the area in the tails of the distribution is a little bit greater. This is the other important one than the area in the tails of the standard normal distribution. Okay, so that because we're using a sample standard deviation to estimate sigma, we don't know what sigma actually is, the population standard deviation. We have to allow for more variability in our t statistic. It has more area under the curve. It allows for more variability under the curve, I should say. And then as your sample size increases, this T curve gets closer to the standard normal curve. So with a big enough sample size, it doesn't really matter. But with small sample sizes, there's more variability with the T distribution. Okay, let's take a look next at what the T table looks like, the T distribution. This is table 7 if you have a hard copy of the text, or it's table 7 if you are in my math lab or in the homework. You can pull it up within the problem, the T distribution. Okay, so we have down the left-hand side is our degrees of freedom, and where that number comes from, that is little n minus 1, the sample size less 1. That's where you go down to, depending on what the problem tells you. Okay, and then where you go across to, well, that's a little bit more involved. Notice here it says this is the area in the right tail. Okay, so let's take, for example, up here, if we have, say, a 95% confidence interval. Let's go up a little bit more. A 95% confidence interval that says that 95% of the stuff is between these two z-scores, or t-scores, excuse me. If 95% is between the two scores, that would leave 2.5% to the right and 2.5% to the left of whatever those t-scores are. And you'll notice in this section the notation t with a little subscript alpha over 2 and negative t with a subscript alpha over 2. Okay? So if I do have a 95% confidence interval, and let's say, for example, I have a sample size of 16, so my degrees of freedom is 15, I'm going to go across to 0.025, also known as 2.5%, see where they meet, and they meet at 2.131. All right, so that's how you use the t-table. Let's do it for my second example at the top. If I have an 80% confidence interval, that means 80% is between these two t-scores. That would leave 10% for the bottom half. That would leave 10% for the top half. So on my t-table, I would go down to my degrees of freedom. For this example, let's say my sample size is 30, so I'm going to go down to n-1 is 29. And then 10% is up here. See where they meet, and they meet right there. 1.311 is the t-score that I would use for that problem. Okay, so now if I go up to the top of this slide here, let's zoom in a little bit there. There we go. All right, so we have confidence intervals using students' t-distribution. We can compute a t-score just like we can compute a z-score. It's ultimately basically the same formula, x minus mu over sigma. That should look familiar from chapter 8. Our degrees of freedom is n minus 1. Again, I've talked about that. And then the confidence interval formula, x bar plus or minus the t-score, because we're in 9.2, times s over radical n. That represents the population standard deviation. Sigma is your population standard deviation, and that's the formula for it when we have a sample distribution, or a distribution of the sample mean, s over radical n. Okay, so this is the big formula for this section. Now we go back to our miles per gallon example, and we are going to construct a 95% confidence interval that leaves 2.5% in each tail for the mean miles per gallon from the earlier example. And in the earlier example, our x bar, our mean, was 24.13 miles per gallon, and then the standard deviation, s, was equal to 3.21. 3.21 is our sample standard deviation. Okay, so if I'm making a confidence interval, an important step, like in real statistics, is to verify that our data is random, small relative to the sample size. If it's very small, less than 30, draw our probability plot to verify that it's normally distributed. So if you check this in Minitab, you should find that the normal probability plot is approximately linear. So that should work out. I'm not going to do that here in this video. If it were class, maybe I would, but feel free to do that if you have easy access to Minitab. But then step 2, we're going to use the formula x bar plus or minus a t-score, alpha over 2, times s over radical n to construct our confidence interval. So plugging in what we know, x bar 24.13 plus or minus our t-score, I'll come back to that in just a moment, 3.21 is the standard deviation. Sample size, if you recall, it was 13, so over the square root of 13. Okay, so to find our t-score, let me scroll down to my t-table here. And what I'm going to do is our sample size is 13, as I already said. We are making a 95% confidence interval, so we're going down to 12 because n minus 1 is 12. Actually, I'm not going to use a highlighter there. Let's point at it. 12. 95% So we're on our 0.025. That leaves 2.5% for each tail. And if you trace the 12 over, you get a t-score of 2.179. All right, so that is what goes into our confidence interval formula, 2.179. Perfect. All right, so when you punch that into your calculator, now I'm just going to do the margin of error first. And in doing that, I get 1.94 miles per gallon, 24.13 plus or minus that. So our confidence interval is 24.13 minus 1.94 is 22.19. And then when you add 1.94, you get 26.07. Okay, so what does this mean, right? This is a statement, an interval about the population. So we are 95%. We are 95% confident that the population, that all cars, because that's the kind of the general thing we were told in the beginning of this problem, that it was a random sample of cars, that all cars have a mean miles per gallon between, and for this I'm just going to round to the nearest gallon, or nearest whole, 22 and 26 mpg, miles per gallon. So in our sample it was 24-ish. Margin of error was about 2, so 22 to 26 miles per gallon would be the average for all cars in this population. Okay, good. In the last section, we also looked at how large of a sample you need to guarantee a certain level of, or to guarantee a certain margin of error with your confidence level. Well, in this section, when we do that, unfortunately, because we're solving for the sample size, we no longer know what the sample size is. So we can't use our t-table with our degrees of freedom. So our best option is to use the z-table. Even though we've already kind of said that the t-distribution is better here, if we're solving for the margin, the sample size, we have to use the z-table. Okay, so in this question, we're asked if we want half a mile per gallon as our margin of error and 95% confidence, what does our sample size need to be? Well, we just solve that error equation for n. So I have the error equation here for you. If you solve for n, and they give it to you in the book, and you should make a note of it so that you have it when you need it for the homework questions. It's your z-score, z alpha over 2, times s divided by e, and that whole big shebang squared. Okay, so there's your formula that you need to do this. If you like algebra, maybe, I don't know, but if you like algebra, you can just substitute into the regular error equation and then do the algebra steps, divide, square root, or square, etc., etc. But you know, it will give you the formula, so you don't need to worry about that. And then I take and substitute what I have for this problem. Okay, I'll come back to the z-score in a moment. We want to be within half a mile per gallon. That's the margin of error. The standard deviation was, let me look that up, 3.21. 3.21, and then the z-score, so and squared, and then the z-score, how do we get that? Well, we can read it off the table at the bottom of the z-table. For a 95% level of confidence, that's a z-score of 1.96. If you type all of that into your calculator, you get approximately 158.34 if I round to 2 decimal places, but we need 159. We need to round that up automatically to 159 cars, in this case, to hit that 0.5 margin of error. All right, that is it for section 9.2. Thank you very much for listening. Work on some of the homework. Let me know if you have questions, and just have a great day. Thanks for listening.